Hello, in this video we are going to work with the scenario that's given in the blue boxes at the top of our screen. We actually have three parts to the problem, and so you see those in the three boxes below. They match up with the three outcomes that we have for this lesson. So our first outcome is that we wanted to be able to write an equation. And so this is our first one. We are going to use the models in our pre-lecture. And you will be given those models. You do not need to have them memorized. Our second one is a question that we will do on our calculator. So this says use our calculator. And our third course outcome and our third question here is where we are going to use Desmos, but we could use a logarithm if you wanted to, or Desmos, a graph. And we're going to focus on the graph here in class to do that instead of using all of the algebra. So first thing I want to do is to read the problem. And so it says the world population was about 6.5 billion in 2009. And if that was growing continuously at a relative growth rate of 1.14%. So keyword here is continuously. And because it is continuously, that is the word that tells me to use the exponential model from my notes. So that exponential model says P of t, population at some point in time, is P0, the starting population, times E with an exponent of RT. So this is our model or our formula that we're going to fill in some values based on this scenario. So in any formula, we still are going to have some variables. So the P of t, the population that we're solving for, that's going to remain a variable every single time. So P of t equals P0 needs to be replaced with the starting amount. So the first number that we're given is a world population of 6.5 billion in 2009. So I'm going to replace that P0 with the 6.5 billion. E is locked in because it's continuous growth, so that is the base with continuous. And next comes R. R always is a percentage, and so I'm going to take the 1.14% given in the problem. I'm going to divide that by 100 to change that into a decimal, which gives me 0.0114. So my exponent on T will be 0.0114 T. And so this is our answer. This is the formula for this problem. Now, the reason why it still has a P of t here is because we can use this formula to calculate any different population. And the reason why it still has a T is because we can pick any year to calculate the population. So I picked 2020, the year that COVID hit, and we don't have a full sense of how hard COVID has impacted the world population, and so I didn't want us to use trends from pre-COVID to predict here in post-COVID times. So it says, if the trend continued, what would have been the population in 2020? So for this, I know that my starting date was 2009. And so if I subtract that out, so I take 2020 and I subtract out 2009, I see that this is 11 years after the start. And so that is a time, so I am going to put that into my formula for t. So I now have P of t, the population at some point in time, will equal 6.5 e to the 0.0114 t. This is calculator friendly. So what we're going to do is we're going to type 6.5. We're going to get E. So that's 2 keystrokes on our calculator. So in order to get E, we're going to have to hit the second And then 2 buttons down from that, so I'm going to put that in a little square. So that's the second button on our calculator. And then we're going to hit the LN button. And so those 2 buttons will work together, and your calculator screen will display E, and it'll display caret key and parenthesis. Because your calculator is very smart. It knows that if you are using E, then you are going to be using an exponent. And so it has you all set up to type in the exponent. And so the exponent that we have here is 0.0114. And instead of t, I'm going to type times 11 because this is to be 11 years later. And so give me a moment. I'm typing that into my calculator. Now, very important, I cannot end my parentheses until after that 11 because that 11 is part of the exponent. I have to get all of that in the exponent. And so my calculator, I hit equals, and my calculator gives me 7.368, etc. And so my original number was rounded to 1 decimal, so I'll go with 7.4 billion. So that is our answer. And so for the second part, we used our formula that we wrote in our first part. So I brought this over. What I did here, and I didn't write this in exactly, that is where I put the 11 years, where the T is. And then you can see using the second and the LN button to get that answer on our calculator. So the next question says, if the trend continued, when would the world population be 8 billion? Okay. So going back to my formula, the population, this is a population. So because it is a population, this is a P of T. So that would make my formula 8, replacing the P of T, equals 6.5 E with an exponent of 0.0114 T. And what I'm trying to figure out is the value of T. How much longer would it take for the population to grow that big? So one way to solve this is to use algebra and to use a logarithm. And that would be the by hand method. And you can watch videos if you would like to refresh that, if you remember that from another algebra course. We are going to use the Desmos graphing calculator. So as we had practiced with algebraic word problems, the Desmos graphing calculator allows us to put in 2 equations, and then we can find the point where those 2 equations meet. So the way that I will put this into the calculator, I will take this side and I will write that as y equals 8. So we talked through in our notes that the P of T is similar to a y value, and Desmos likes it as a y value. So when we plug this in to the P of T, we were plugging in saying that y is 8. I'm also going to take this half of the equation, and I'm going to say y equals 6.5 e to the 0.0114x. And so I'm replacing that x, t with an x because Desmos likes x and y, and that gives me 2 formulas. So each half of my equation, the left of the equals, the right of the equals, becomes its own equation in Desmos. So here is my Desmos. Let me make that a little smaller. There we go. So typing here, I'm typing y equals 8. Now, I just want to show you, if I just type 8, you don't get that squiggle there, and nothing happens on the graph because it doesn't know if it wants x to be y or if it wants y or x to be 8, y to be 8. It doesn't know what 8 means unless you tell it a variable. So we have to tell it y equals 8 for it to understand. Click in box 2 here for my second equation. So this is where I have 6 point, with my y equals 6.5, And then you can use E right off of your keyboard. So E. And then you can use the caret key right off of your keyboard. So I'm using Shift and then number 6 to get the caret key. And you see my cursor move up there to the exponent position. 0.0114x. So I have blue was my first line, and you see that on my graph. Green is my second line, and you see that on my graph. And I'm going to move my graph down here a little bit so I can see that they're meeting over here. I'm really close. I'm going to zoom out just one. Now, this particular population growth is so tiny that it looks linear. And we'll see some in the future, but it truly is a curve. If we zoom out a lot, we would see the curve. I'm going to do that later. But right now, I'm interested in when do these lines meet. So if I click on a line, I get a point there. Click on the point, and it gives me the ordered pair. So 18.2148. So let me get rid of my decimals for a minute, and then we'll write this in. So 18, here we go. Ordered pair 18.218 and 8. Make sure I have that. No, 214. Let me fix that. This was a 4. All right, so we're going to round somewhere and we'll say 18.2. This is our X. This is our Y. Looking back, our X was our T. And so 18.2 years. And our starting year was 2009 after 2009. So if I want, I can go on my calculator, 2009 plus 18, and that would be in year 2027. Now, that was if the trend continued, and as we all know, the trends aren't really continuing because we had COVID come and interrupt everything. So it may not be the case, and we don't have a long-term growth rate at this moment because we've had, different waves of the pandemic. And so we'll get there, and we'll have more up-to-date data. Bringing Desmos back, and I want us to curve out. Once I zoom out a bunch, you start to see that this green exponential is definitely curved instead of straight. And I just wanted to show you that because we had talked about that one of the characteristics of an exponential is that it's a curve. And this is a growth curve, so it is curving upward, and we will have decay curves that curve downward as well. So that problem takes us through the 3 outcomes that we have. So we created our equation, we used our calculator to figure out a value, and we used a graph to solve for time.